Okay, hello everyone. My name is Cai Kui. Welcome to the 5th talk of the online seminar series, Information Theory in Singapore, ITIS. And also welcome to the virtual Singapore. So behind me is another landmark of Singapore, the super tree grove at Gardens by the Bay. And it becomes even more amazing during the night with the Christmas light decorations. I think Kees may have seen this last year, right? And
Yes.
so anyway, although the world is still suffering from the coronavirus, let's hope this pandemic goes soon, and you all can explore the amazing Singapore by yourself. So the Information Theory in Singapore seminar series is jointly organized by Han Mao from NTU, Mai Hu from NUS, and me and Tan from SUTD. So today is the 5th talk, which is also the closing talk this year. We will set up the 2021 schedule soon, so it will probably start in late January next year. And again, please keep your microphone and video muted during the talk. If you have questions, you can put them into the group chat. So we will address the questions in the Q&A session at the end of the talk. And now it is my great pleasure to introduce Professor Immink as our speaker. So Professor Immink, Kees Immink has made tremendous contributions and pioneered and advanced the era of digital audio, video, and data recording by designing various coding techniques of digital audio and video recording products, including CD, CDR, CD-ROM, DCC, DVD, and Blu-ray disc. He co-authored around 250 papers on communication and information theory, and holds about 70 US patents. He has also founded Turing Machines Inc, an innovative startup focused on novel signal processing for solid-state memories. And he has received numerous prestigious awards, including the 2017 IEEE Medal of Honor, a knighthood on year 2000, a personal Emmy Award in 2004, the 1999 AES Gold Medal, the 2004 SMPTE Progress Medal, the 2014 Edward Ryan Prize for Technology, the 2015 IET Faraday Medal, and the Golden Jubilee Award for Technological Innovation by the IEEE Information Theory Society in 1998. He was introduced into the Consumer Electronics Hall of Fame, elected into the Royal Netherlands Academy of Sciences, the Royal Holland Society of Sciences, and the US National Academy of Engineering. So it is our great pleasure to be able to invite Professor Immink to give the closing talk of our seminar series this year. The title of his talk is Innovation in Constrained Codes. Let's welcome Professor Immink.
Thank you. Thank you, Chai Kui, Professor Chai. Thank you for your kind words as the introduction. First of all, I'd like to thank the committee for asking me and introducing me in this series of very, very nice talks. I have followed 3 of them because the other 2 were not in my time schedule. They were at 2 o'clock at night, and that's a little bit late for me to do information theory. But anyway, I really enjoy all the talks that I heard so much, and I really like you to repeat it next year. But you already have mature plans for doing that. So, thank you again. My talk, the title of my talk is Innovation in Constrained Codes. Of course, we all know the term innovation, and it doesn't need any introduction, but the term constrained needs, or constrained codes, needs some, well, maybe some explanation. The term constrained codes was introduced by Shannon in 1948, and his name was input restricted channels, or better, noiseless input restricted channels. So there is no noise, there are just constraints or limitation on restrictions on the ones and zeros, or the ones and zeros or the twos or the threes that you produce for the channel, because there are good reasons for doing so. And I will show you what kind of reasons there can be to use constraint codes. So let's be very precise. Most of the information theory, or well, a big part of information theory, has concentrated on correcting errors in noisy channels. Constraint codes do not do that. They have no error correcting capacity. They, one sometimes can say, they have the capacity of avoiding errors, not of correcting errors, but to avoid them. Let me show you in the next slide for a few examples what I mean. Yes. So the first sentence is very strong. Constraint code is of existential importance in most digital storage and communication units. I said existential, so I mean that without those codes, the channel could not exist as a channel. It would lose its meaning. Constraint codes, and I will explain you in the next slide what I mean with that, with the existential importance. So they enforce limitations or restrictions, constraints on the sequence of signals in order to make communication possible, to limit interference between channels, for example, or to other subsystems of a channel, to enable clock synchronization, shape the spectrum, the signal spectrum, and so on. You can ask yourself, why should I do that? It depends. Why should I shape the signal spectrum? We will explain that in a few examples, for example, for modern data storage systems or so. Let me first explain the first sentence of the existential importance of constraint codes. It shows a very ancient communication system, very ancient. This is the communication system I have in mind. This person is using smoke signals to signal messages from one place to the other, okay? And he uses a blanket, as you can see, to stop the smoke or let smoke go. Okay, that's the signaling. So the smoke could be a 1, and the non-smoke is a 0. So if his blanket is too long on the fire, so he sends out too many zeros or ones, whatever, then his blanket will be in fire and his whole communication system will fail. It will not exist anymore. So that's what I mean with existential existence, with existential importance of constraint codes. Because a constraint code is a means to limit the number of ones or zeros that are sent out in a consecutive fashion. So they limit the run length, so to speak. So this ancient person here in the picture, he doesn't know about run length limited codes, but probably he is using them in avoiding to that his blanket will be in fire and his communication channel will stop anyway. So what kind of applications of this constraint codes are now being used in modern technology? This is ancient technology, but anyway, you will see there is not so much difference between the ancient technology and the modern technology. Let me see some applications. So applications are now found in solid state memory, for example, in flash. The Internet of Things for energy harvesting. I will explain you in a few sheets later. I will explain what that means. Invisible light communications, and also in very modern DNA-based storage, and in still modern magnetic disk and tape drives, and in optical disk drives. So these are just applications that I found, and on some systems I actually contributed a little bit to the constraint codes. So what kind, that's the next sheet, what kind of constraint codes can you find? Because this was just the applications. But what kind of codes do we find? We can find, for example, Runlength limited codes. So we already saw an example of the Runlength limited code with the ancient person with the smoke signals, because his maximum run length should be limited. Runlength limited can have a minimum run length and a maximum run length, but I will introduce that in a few seconds. We have, for example, comma-free codes. That means that a comma is a sequence of ones and zeros. It can only occur on very specific places, like a comma, and should not occur anywhere else in that sequence, because otherwise the synchronization of a sequence should be lost. We also have, these all were in the time domain, but also you will find codes that have spectral nulls. What that means in the spectrum itself, in the power spectral density of that code, specific frequencies should be avoided because they could interfere, for example, in optical recording. They interfere with these servo systems, and if they interfere too much, tracking of the information is impossible, and the system would be non-existent. It should, well, it would skip in a moment and it will stop. You also have, and this is very interesting stuff for people who like to do some deep mathematics, and it's called two-dimensional constraints. So assume you have a chessboard and certain patterns of the chessboard are not allowed. For example, you do not allow, for a technical reason, that two white places are next together, or two black ones, or certain crosses are not allowed, and so on and so on. It's a very difficult issue, and we will not talk too much about it. But anyway, there's still very interesting work going on, and we will see. Then a new issue that we introduced a few years ago have to do with Pearson codes, and I will explain that in a few seconds later. So what is the focus further? Well, actually, Shannon, already in 1948, he introduced the noiseless restricted channel, and he computed the capacity. So if you have, again, like this ancient person, you have a maximum run length constraint, that definitely means that you cannot send out all arbitrary sequences, and it means a limitation of the capacity. So capacity computations are important part of the constraint codes. Then, of course, for engineers, it's very important to have fine, good methods for code constructions. And of course, you like to have a code construction that approaches channel capacity that was computed, and without too much complexity of the encoder and decoder. This is common sense. You also have, in real-life channels, you have the concatenation with error-correcting codes. How do they work together? Do you first have a constraint code and then an error-correcting code? What kind of error-correcting code? Or do you have first a constraint code followed by an error-correcting code, or the other way around? And the other way around is called the reversed concatenation, because normally, in most systems that I know of, you first have the error-correcting code and the encoder, followed by a constraint code that adapts the outgoing sequence to the physical difficulties of that channel. Let me look at the at Shannon's paper in 1948. And of course, we all know Shannon's figure 1 of his seminal paper, but normally in a room, I would ask, does anybody know Shannon's figure 2? Probably nobody knows Shannon's figure 2, but in the next sheet, you will see figure 2. This is figure 2 of the Shannon's paper, 1948. And the section is called Noiseless Input Restricted Channel. And Shannon introduced the noiseless capacity. So you have certain constraints on the ones and zeros. Shannon came up with a telegraphy signal where you have dashes and dots, and certain dots may not be followed by dashes, or the dots not by dashes, and you have letter spaces and word spaces. And actually you can put all these constraints, and Shannon showed that in his paper. You can put all these constraints in a diagram, and you get a kind of Markov or diagram, or you can put it in transition matrix, and you can have certain states, and from a certain state in that model, you can jump from one state to the other, and also send out a 1 or a 0 or some other symbol, and so on. And you can, if you have these constraints, you can actually compute the capacity. And in most cases that I know of, so this is all still from Shannon, in most cases you can compute the capacity by computing the number of sequences as a function of the length of the message. And what you do, so that is capital N as a function of n, where n is the length of the message. What you do is take the log2 of the number of messages available, and you compute the limit for very long, infinitely long n. Fortunately, for many channels that I know, the number of messages as a function of n is growing exponentially, here in this case with lambda. And then, so you can just compute C by taking the log2 of lambda, and that's essentially what you can do. The difficulty is sometimes that it is not so easy to find the number of n, and you need to be an excellent combinatorics mathematician to find n, capital N, as a function of n. But for some constraints, like the Runlength constraints, was already done by Shannon, and it can be done much easier than, well, it can be done very easily, because, well, you can write down a recursive relation to find n. Let's focus on Runlength limited codes, okay? So, just like in the ancient person, Runlength limited codes avoid the generation of long run lengths and short run lengths of ones and zeros. And a run length is the number of consecutive ones or zeros. That's the definition of a run length. So there should be a limit on it. And the run length should lie between d plus 1 and k plus 1 bits, where, of course, k should be larger than d. Applications of run length limited codes have been found in essentially all magnetic disk drives and in all 3 generations of optical recording. So they have played a key role. They have been of great importance. Quite interesting, I think, that also application of run-length limited codes are found in DNA-based storage, where you can find a quaternary alphabet. The binary coding technology of run-length limited codes is very mature, and it is very hard to find, I think, new entrants for improving, let's say, the rate of the code, or improving the constructions of these codes. Let me, because they have been so important, let's look at the history of run-length limited codes. For example, a very early magnetic code for magnetic recording was invented by Aaron Miller in Ampex. Ampex was in the 50s and 60s and 70s a huge company working on video recording and also on digital video recording. And this Mr. Miller invented the modified FM code, where you have D is 1 and K is 3. So at maximum 2, or at minimum 2, and at maximum 4 Runlength, and it was invented in 1963, so very mature and very old. Fryman, oh yeah, what I did is actually I also listed the company for which these persons, the authors, were working, and you will see that most of the work has been done within IBM, not within Bell Labs, AT&T, where Shannon was working. All these work has been done by IBM engineers and scientists. Peter Franasek and IBM, he constructed efficient decay codes for magnetic disk drives. And finally, much later, 15 years later, Adler, Coppersmith, and Hessner, they came up with an algorithm called the ACH algorithm that from Markov source, that describes the constraints, for example, for decay constraint, but for any constraint, you can efficiently and systematically design codes by so-called state splitting. So also this method is called the state splitting method. This paper is very important in this field of run-length limited codes or for constrained codes, because they prove that you can always design a code with a certain number of states, and very, very interesting, but not easy to read this paper. Let me warn you, if you think that you can read it within an afternoon or so, it's not so easy. For so far I know, the first application of run-length limited code was in the IBM disk drive, introduced in 1970. That was the MFM code, and the 2.7 code, which was introduced 10 years later. Let me look at the MFM code, this modified frequency modulation. Let me take a look at it, because it is so extremely simple that if you look at it, you will say, my goodness, is that all there is? Yes, that's all there is. It is a rate-a-half code, and it translates one input source word to two output source words. Okay, there should be at least 1 0 between ones. That's the construction. And as you can see, a 1 is always translated into a 0 1. Okay. But a 0 is translated into an X and a 0. And the X depends on the preceding bit. If the preceding bit is 0, you can and you must use a 1. If the preceding bit is a 1, then the X will be 0. And it takes a little bit of puzzling, and you will see that with this very simple construction, that the constraints, the decay constraints are D is 1 and K is 3. Very simple, very straightforward, and you can see that the encoding is slightly complex, but the decoding is very simple, because you can see that the last bit of the 2 bits are equal to the source bits. So that's kind of systematic code, so to say. Very simple, but the codes that were constructed much later, this was in 1963, and given the hardware in 1963, it was already a very complex code, remember. The next slide shows you, just to show you how complex the hardware and the electronics were in those days. This was introduced in 1956. And this is a huge machine, as big as a washing machine or a laundry. It's enormous. It was introduced in 1956. It has a capacity of 5 megabytes. I don't know the price in US dollar. I will look it up when I'm bored time. And the code was called biphase, which is a rate-a-half code, and which has is a DC-free code, has no spectrum content at DC. And this changed the world actually of computing. You can't believe it, that this enormous machine, and if you look at the computers in the 50s, was also very complex machines. But this this was the very first disk drive and mass storage product available in those days. And this thing actually changed IBM from a company that was making mechanical tools into the largest computer manufacturer of the world. They became very important because of this machine. And the next sheet also shows you a product made by IBM that was introduced in 1979. The capacity is 1 gigabyte, which is around the capacity of 2 compact discs. Actually, it was introduced in the same time as the compact disc. So this huge machine, this washing machine, can store the same amount as 2 compact discs. The price is around $100,000. The weight is 30 kilograms, and it uses a DS2 and KS7 rate-a-half code, which was designed by Peter Franacek in the 70s. Next products where you can find Runlength limited code is the EFM code, 8-to-14 modulation for the compact disc, introduced in 1982. EFM Plus, this is also a DS2 KS10 code, introduced in 1995. And the DS1 KS7 code, introduced in the Blu-ray disc. And the reason for using Runlength limited code, well, the maximum run length is easy to understand because it has to do with the fact that you need clock synchronization from the transitions 1, 0, 0, 1. So if this transitions is too long absent, you cannot synchronize the bits. The minimum run length is very difficult to explain, but it has to do with the replication process of these plastic CDs. And it's very difficult to manufacture small bits in these plastic discs. So you have to use coding technology to make the discs, the bits, slightly longer than you have with uncoded information. Quite interesting that in modern, very modern actually, not yet on the market, products, also Runlength limited codes have been introduced. For example, in DNA-based storage, you must have a combination of, well, there you have a quaternary alphabet, A, C, G, and T, and some run lengths are not allowed because then the lifetime of the molecules of DNA will be limited. So here also you will see the existential difficulties. And just to give you an idea of the amount of storage that we can have, that in one pint of beer or so, you can store 10 to the power 21 bytes, which amounts to, well, the whole internet at this moment. So it's huge. So in DNA-based storage, you have an input file. You go to a manufacturer who can produce those molecules, and with a lot of money, you actually get a container full of these DNA molecules that you can read in the same way as the people can now read that you have corona or not, essentially the same equipment. And then you can, with your decoders, you can restore the information again. So very interesting to see this back to apply well-known technology to this modern data storage medium. Spectral shaping codes have been used in all kinds of systems: AC coupled cable system, visual light, optical disc recording for avoiding interference with server tracking, and also a magnetic tape recording, because the magnetic tape recording has no response near DC, the low frequency area. So then the spectrum here you can see on the horizontal axis, the frequency of the power density function, and the vertical axis you see the power density function, and you can see that the low frequency end, the spectral content is 0 or very close to 0. Design of these DC balanced codes is very interesting, and and a topic that's still very much alive because it is not so easy to efficiently encode arbitrary data in code words that have, for example, equal numbers or ones and zeros. Applications of these codes you can be found in the R-DAT digital audio tape recorder made by Sony in the 80s. It didn't live very long because the audio the music industry in the United States didn't like it, so it was essentially a commercial blooper. But anyway, also in the digital compact cassette that was introduced by Philips in 1985, also was commercially seen, it was a blooper, but from information theoretical view, it is exciting because it was using DC-free or spectral shaping codes. Let me look on the, so what I just said, balanced codes, we can use lookup tables, and we have the famous Knut algorithm for translating ones, arbitrary ones and zeros into a code word with equal number of ones. You can have algebraic coding, and you can have all kind of guided scrambling, and you can also have balanced code with error correction. These kind of things, so balanced codes, let's say codes with a given weight, with some distance, have been a focal point of mathematicians for at least 30 or 40 years, and still some people are working on it and try to find the exact number of code words with some. I also like to give you some idea of what we have been doing lately. So we send out some code words, let's say X, and we receive a code word X plus V. That's the normal situation if you look at the 1948 paper by Shannon. So you send out an X, and you receive R, which is equal to X plus V. That's the very simple situation when you're working, for example, in NASA, when you send out satellites to Venus and Mars, then you only have noise. But if you're working in physical things like magnetic or optical disk drives, then the received signal is perturbed by other unknown parameters. And here in my sheet, you can see that the code word has an unknown gain, so that's what's called A, and it also has an unknown offset called B. So this is slightly, so this, the received vector is, so it's scaled by an unknown gain, and it's offsetted by an unknown B. So essentially, well, it's slightly different from what Shannon did in 1948, but in my expertise, in my field of work, this is much closer to the reality than what Shannon did in his 1948 classic. It's, in my view, it's an excellent start, but in my products, Shannon's view doesn't match actually. So of course we can try to have a good estimate of A and B. For example, if nothing really changes in the channel because it is very slow changing, then you can have automatic gain control to find A and B. What you can also do, but it will cost you capacity, is every 100 bits or 50 bits, you introduce some reference symbols that you know beforehand are 1 or zeros, so that you can actually estimate the unknown gain and offset. You can also have balancing constraint, but all these things are expensive, and we try to look at the at ways to find out. And of course, in the Shannon case, where you have only X plus V, usually you have some kind of maximum likelihood estimate of X to find, of R to find X. And you use some, let's say, some measure of likelihood. For example, you can use Euclidean distance, but to find between R and the allowed code words in your code book and find the closest vector, and you call that the one that was sent. That's the Euclidean distance. We introduced a new distance and we called it the Pearson distance. Actually, the Pearson distance was already known, but it has never been used for this kind of channels where you have unknown gain and offset. For example, let me show you what will happen. Okay, you send out, for example, code words of length n. They have a quaternary, like in DNA, you have quaternary signals, 4 levels, and you have some noise. The noise is given on the horizontal axis. This is the very regular waterfall curves that we are all very known of. Okay. The curve below was used as it was used by Shannon in his Shannon paper. There's no mismatch. The only unknown parameter is just noise, no noise. So this is the lowest curve. This is the best one that you can find. Everything is fine and everything is Shannon-like. Okay. Now we go to this curve, the upper curve, and we changed slightly the amplitude of the incoming signal to 7%, and we had a 7% in the same way offset, B. And you can see that the bit error rate of the word error rate is going up. Yes, it's really bad. Actually, you only need a very small extra change and the decoder will fail forever. In the middle curve, actually, that's what we call the new detector, we use the so-called Pearson distance. And whatever A and B will be, it could be 1,000, it could be just a half, or B could be 1,000, or it could be any value of A and B, and the word error rate will be the same for the new detector. It's completely independent of A and B. Of course, you can see that it has a significant advantage if A and B are known, as you can see, because it is better than the upper curve. But you can also see that this curve is worse than the Shannon model, where you have no mismatch. Okay, so you have to pay a certain insurance premium to be independent of A and B. Well, that's actually normal for, let me say, for real life situations. You can get, in engineering situations, you can get nothing for free, and you have to pay a slight price in signal to noise ratio when there is no mismatch. But you can feel very comfortable, because if your channel has a certain mismatch, then you know that your word error rate will be the same forever, will never change, will be independent of A and B. This is Carl Pearson. This is a diagram, and if you have absolutely nothing else to do during the times of Corona, you should read the biography of Francis Galton. He is very interesting because he introduced the correlation coefficient, and he introduced regression analysis. Nobody actually knows what the term regression analysis means, but Francis Galton, had the idea that the quality of people, I mean IQ, intelligence, was actually regressing over the years and over the many generations, because poor people, that's what he wrote, because poor people had too many children. Okay. That's why it's called regression analysis. Okay, this is his ideas, and definitely not mine, and I believe that not many people have this kind of ideas. But it is interesting to know what a very rich person like Francis Galton, his fortune actually was inherited by Carl Pearson, who did many other things, important things in statistics. And it's very, very interesting to note that many very famous statisticians like Pearson and Galton have such a brown history, we call it. Okay. Anyway, I will, because I will not go into the Pearson distance test. Anyway, the Pearson correlation coefficient, as we already know from statistics, is something like this. And the Pearson distance is 1 minus the correlation coefficient between the two factors. And that's what we used in the diagrams, in the diagram that I showed you. And in order to use the Pearson distance, you cannot use any code book that you like, because clearly, if an offset, if the detector cannot see any offsets, then he cannot see any the difference between an all-1 code word and an all-0 code word, because they are the same actually, because it's just an offset between the two. So if you have the all-0 code word, then the all-1 code word cannot be used, because this Pearson detector cannot see the difference. And also the same applies to multiplicative versions of code words. If one code word is in the code book, then a code word that can be found by multiplying that same code word should not be in the. So you have to find code books that can be used in conjunction with Pearson distance detection. And so that means that in order to use the Pearson detection, the Pearson distance detection, you should compute the size of these Pearson codes, and you can look into combining Euclidean and Pearson distance with maximum likelihood and so on. And we have done quite some work with Jos Weber and with Professor Chai and Professor Skychek and Renfei Bu and many others. And let me look also at a new thing that we did during the last years, and that is called energy harvesting codes for the Internet of Things. And usually they are very tiny pieces of electronics, and these tiny pieces of electronics in your refrigerator or in your bicycle, wherever they are used, usually have no cable connected to the energy central, or they have no battery. So they need some energy from the transmitter that carries the information. So the transmitter that sends information to the product in your devices should also carry energy. That's interesting. That's a thing that has never been studied by Shannon and others. This is a very new and interesting topic. And so, for example, a minimum numbers of ones, if ones carry the energy, are required to carry sufficient energy over to the receiving part. For example, you can say that you can use a sliding window LT constraint, and you can say that the number of ones within any window of L consecutive bits should be at least T. Okay, that's fine. Of course, you can send other sequences, but this is also a very nice definition. And given this constraint that you like to see T ones in L consecutive in a window of any window of L consecutive windows, you can define a state diagram and you can compute the capacity. Sure, for small L and T you can do so. An example is given here. Here, this is a six-state diagram which portrays the constraints of L is 4 and 2 is and T is 2. So any window in any window that will be produced by this machine, you will find at least T zeros. That's fine. But if you go to larger L and T, you will see that the number of states will grow exponentially. And then it will be very hard to compute, for example, the capacity. As said, sure, also in this case, the capacity grows exponentially with the number of messages grow exponentially with the message length, and you can just compute the capacity. But for the constraints of the Internet of Things that you just did, this is extremely difficult because of the large number of, it's also difficult to find an estimate. So if there are some people who like to work on this, you're more than invited. So let me go to the final sheet of my talk. And the constraint, well, I hope that I show you some historical things, not too many, because there is a long history in these constraint codes. And as you have seen in DNA-based storage and in the Internet of Things, you will find many, many applications of constraint codes where you cannot just, because that's the essence of my story, where you cannot just use any sequence of ones and zeros, but where you have certain restrictions, and the restrictions make it an interesting topic for information theorists like yourself. Thank you so much for your attention.
Okay.
Of course, if there are questions, sure.
Yeah, thanks, Kees, for the great talk. Yeah, any questions from the audience? Yeah.
Yes, Kees, that's a great talk. You know, one thing, at least one thing I learned from your talk is why there's a minimum run length requirement. Okay, this is quite mysterious to me. Okay.
Yeah, it is mysterious, really. It has to do with the real physics of optical recording, and it has to do with the fact that replication of very small bits, because they are impressed in the plastic, is much more difficult. Of very small one is much more difficult than larger ones. If you have played with sand on the beach, maybe you can remember it's very difficult to get the sand out of the vacuum the containers. If you use as a child, you use it probably.
Yeah, speaking of physics, you know, the run length code has never really been a research direction of myself. But I did wander into this area about 15 years ago, okay? And I look at the problem from a physical point of view. Okay? So we know that it's fine to start with the discrete time channel, but we know that the real channel is actually a continuous time. Okay? So imagine that you know, you're trying to read out something, read out a waveform from a turntable, okay? And the speed of the motor of the turntable is not very stable, but that it is bounded by some lower limit and the upper limit. Okay, this we just start with this model, and the paper that we eventually wrote actually has the title "Reliable Communication in the Absence of a Common Clock." Okay, so there's no common clock between the sender and the receiver, and you need to figure out what the waveform that you sent were. Okay, with the stretching and compressing, you know, introduced by the instability of the motor. Okay, that's the statement. Okay, so actually the notion of resynchronizing from time to time is not really there, because you can just look at the whole sequence. Okay,
yeah.
And then but the very interesting finding was that even without any notion of you know, self-synchronizing periodically, it turns out that run length code is just the optimal coding strategy for such channel. So that's actually quite a delightful surprise.
Yes, it's interesting what you say. I have seen more of those papers, and actually what you are describing is that you receive lots of data without any synchronization and so on and so forth. Actually, you have the very same situation in DNA-based storage, because you have information written on very small molecules, and millions and trillions of these molecules are in a container, and you shake them and you shake them, and you don't know where the information is, and you just have to find out where your data is. Essentially, that's what I feel that you described in your paper. Is that true, Raymond?
No, well, we just considered stretching and compressing the waveform.
Oh, I see. Okay. Oh, they are still connected to each other.
They're still connected to each other, exactly.
Ah, okay. Well, DNA-based storage is much more complex than that, because they are not even connected.
Right. Okay. It's a different model.
Yes, you have a piece of paper, you threw it together, and then you have to find the message again. Okay. That's an interesting paper. That's an interesting issue.
Yeah.
Yeah. Thank you for your question. Thank you. Very interesting.
Thank you.
So, any other questions?
Kees, I have a question. So I like your codes based on the Pearson distance very much. Just want to ask about some intuition. So the Pearson distance is like I guess essentially robust against gain, right? I mean that's like the gain and offset, right?
Correct.
What was the intuition behind like the price you pay? Like when you showed that curve, you showed the no mismatch, then you showed the Euclidean distance mismatch, and then you showed that for any gain and offset, the Pearson code is in the middle. But can you give intuition for what's the price you pay for the? I mean, there's some SNR price you pay, right?
Yes. Yes. Correct.
If you give some
Yes.
intuition for that, that would be nice.
Yes. Well, if I would have a blackboard, I could write it down, but it has to do indeed that the minimum distance, the minimum, well, the word error rate is always determined by the minimum energy between the difference of sequences, and that's and
right.
the Pearson distance is not using the right metric for an optimum detection in when you have noise. Euclidean distance has not by definition, but it can be shown that it is the optimal metric for using in the case of, I believe, Gaussian noise, but maybe even other kind of noises. But anyway, so if you say that, if that's by definition the optimum, then all the other metrics or object functions that you use to recognize and send code word must be worse.
Yeah. Okay.
Yeah. But it is not so easy to just show it without using a blackboard, right? It is so. But anyway.
Yeah, I mean, I guess some of it come from the constraint, right? I mean, if you want to define good sets of codes based on the Pearson distance, right? You mentioned there were some constraints.
Yes, this is why you use constraint codes, because if you want to apply Pearson distance, because you like to be, well, you like the detection result to be independent of unknown offset and gain, then of course, by definition, such a detector cannot see the difference between a signal that's high or low. And so it cannot, it's remarkable. It's, you cannot, this detectors cannot distinguish between an all one word or an all zero word, because the difference is only an offset.
Exactly, yeah.
Yes, and very funny, because, well, it's just like, yes, it's just like an invisible person. He is also invisible. Did you know that? Yes.
Yeah.
He is blind. An invisible man is blind, but we can discuss that later. Anyway.
Okay, thanks. Thank you, Kay.
So if
yes, sure.
Kees, there are, things that are connected to decay thing, like intertransition constraint inputs to Gaussian channel, which is now, it's quite an old word, means that you can use only bipolar signaling, but you are limited by the intertransitions. It cannot be too short. And now it's very, very relevant to faster than Nyquist signaling. That
fantastic.
Very relevant. At that time, I mean, it works in the 90s. I myself did with Hayat. So it's very much related, although it's continuous. The signal could be continuous, bipolar, but intertransitional constraint. We have, quite nice techniques of that time, decades ago, to look at the capacity.
I see. Thank you, Shannon. Thank you, Shlomo, for the remark. Thank you.
So we got a question from Wang Yixin so Yixin, you want to talk? Okay, I read out the question for you. So I was wondering, are there any specific criteria to evaluate the energy harvesting code in terms of the energy consumption?
We are talking about the energy harvesting codes.
I think so, yeah. So he asked about any specific criterion to evaluate the code performance, yeah.
Oh, you mean this topic? I don't know.
Oh, yes.
Most of the work.
Can you hear me? Hello.
Hello, now I hear you. Yeah, sure.
Yeah. Hi, Immink. I have known you for a long time. I really admire your research work. I don't know. Yeah. Also, it's very the honor here to listen to your talk. It's very interesting and informative. So I really feel quite into this topic. It's like energy harvesting codes for Internet of Things. So I feel it's quite interesting because I never thought of the codes can be seen in terms of energy consumption, right? So I really wondering that is there any if we want to evaluate the code, is there any criteria that can be used to evaluate it in terms of this energy consumption?
Sure. Most of the work is still in very much of theory, and most of the things that has been done in the academic world, it has not yet concentrated too much on complexity. Of course, complexity is extremely important, and also, as you say, the energy consumption of these products. So if you look at the specifically of the receiver, it should be as simple as possible. So maybe just a lookup table to convert an incoming signal to a decoding signal, and it should also be possible to transmit. But transmission from the Internet of Things to a big receiver is different to the other way around, and so the complexity of the home station can be much more complex than that of the product itself, I think. So it's an asymmetrical situation, and I like your question very much, and I wish I could answer it in a few simple words, but it's not so simple as that. And up till now, what I have seen in this area is that most people have concentrated on designing simple codes that can be decoded at the reception side in a simple fashion, and also that the transmission rate is close to capacity if we can compute that, and so on and so on. But this asymmetrical situation, I think we should, well, more work should be done. Actually, that's quite clear for me. Thank you.
Thank you for answering my question. Yeah, I think it's really interesting. I do think it might be they are kind of because we know that the code word, maybe in terms of this energy consumption, in evaluating this energy consumption, there might be some bias in different positions of the bits in the, the bits positions in the code word. So that might another things maybe we can get go into that to know maybe there are more specific ways to show that this code is better than the other code. Yeah, but I just think this is quite interesting. I really want to ask you this question, and thank you for answering me. Yeah.
Thank you. You're more than welcome.
Okay, Yixin, can I check? Are you with NTU?
Yes, I'm in.
So I guess you are the one who has done some DNA experimental study, is it?
Yes, I am. Yeah.
Okay. Yeah. Great to see you today. Yeah.
Yeah, me too. Me too.
Yeah, you've done quite some good work. Yeah.
Yeah. Thank you.
Yeah. And so, any more questions for Prof. Immink?
Yes, Professor Immink, thanks for your presentation. My name is Pampa. I'm a PhD student of Professor Cai Kui. As you may know, we are doing some research about resistive memory, which has 2D structure. So recently, I'm designing some 2D constraint codes for our RAM. So can you share some 2D constraint codes as some examples or experience for me?
I couldn't understand the question. Could you rephrase it, Cai Kui? Because, well, I can understand you.
Yeah, I think Pampa's question is, she's now trying to design some two-dimensional constraint code for some emerging memory, RAM, and so she would like to know is there any specific design code construction concerns specifically for the two-dimensional constraint code? Yeah.
To my best knowledge, there is no such a thing as a systematic design method for two-dimensional constraint. It's this two-dimensional constraint things is a very, very complex issue, and it's sometimes extremely, it's even difficult to give an estimate of the capacity or anything. So you can put down some very simple constraints in 2 dimensions, and the situation can be extremely different than in the other way around. So again, to my best knowledge, there are no such a thing as design methods for 2-dimensional constraints.
Yeah. So the capacity calculation, yeah, can be very complicated for 2-dimensional constraint code, right? But code constructions, I think there are some works in the literature already, huh? Yeah. Yeah.
Okay, Lee, thanks for your
okay. And so, any other questions?
Oh, hi, Prof. Immink. It's a great talk.
Hi, Tom. How are you doing?
Yeah, I'm fine. Just have a questions on some slide earlier than this slide. Can you turn it back for the balancing things?
Okay.
Oh, there you go. Yeah, just
okay.
The next one.
Back.
Yeah. The next one on the. No.
The next.
Yeah. This one.
There is no.
Yeah.
This is it.
The one just now on the diagrams that you show for the coding method, is it? The vectors R and V X. Then
this one.
Yeah.
Okay.
Oh yeah. So I'm just concerning here why you say that is the. I mean the solution here is it expensive? I mean expensive in terms of what? Yeah, like the redundancy to do the balancing constraint or what?
If you have balancing constraints, if all code words have the same number of ones and zeros, then in the Euclidean distance, the offset will be is irrelevant. Okay, and the same applies to the gain actually. So if you, it's very interesting, but that means that if you use equal weight codes, fixed weight codes, okay, and you apply Euclidean distance, then the reception will be independent of A and B. Just give it a try if you have 5 minutes time.
Oh, because I didn't see it for the Euclid distance, because I thought normally to do the balancing constraint that the cost is not expensive.
The balancing constraint. Yes. If that depends on how you look at it. If you if you are accustomed to rate a half code or a rate a third code, then 5% is nothing, of course. But anyway, that's the term. That's your question. It has to do with the being expensive and balancing. That depends, of course, on the length of the code word, because the redundancy is approximately half 2 log of n something.
Okay.
Most and the best algorithm, CRUD algorithm, is doing a factor of 2 worse than the capacity. But anyway, that means that if you have code words of 16, of n is 16, then you lose 30% or so of your capacity, which is quite a lot.
Oh, okay, I see. I see, because
because to my best knowledge, if you go, of course, if you go to code words of n is 1,000 or 10,000, sure, then the constraints are less. But then, because the requirement that you have actually here in this formula means that A is unknown but constant within that code word.
I see.
And if the code word is getting longer, then from a physical point of view, then also you may expect that A will change during the code word time. And that's what you don't like. So the longer the code word, the more likely it is that the A or B will slightly change during the reception of that code word. So these Pearson codes, I think, because they assume that gain and offset is constant within a code word, can only work in a physical environment where the code word long is not 10,000 or 100,000 bits long, because that's my impression. It should be small. Oh, and then if code word length is small, then the constraints are expensive.
Oh. Yeah, okay, thanks for detailed answers.
Yes, you
I have another question.
But you agree with me on this?
Oh, yes, I agree. Because normally, I usually assume the code word length to be like very large, like as you say, like 1,000 or millions. So so I usually treat the values that logarithm is like small. So
yes, then then sure. It's essentially goes to zero, the redundancy.
Yeah. But, and also, can I add on, because for this flash memory, actually we are not talking about the binary code. So for the binary code, the redundancy for the balance constraint is relatively small, but for query code, for strictly balanced query code, the redundancy is not, is still quite significant, with respect to flash memory. And even with the balance constraint, actually the performance of the detector is not very satisfactory in view of such kind of channel. Yeah, so this is my understanding. Okay, so Tan, you have another question?
Maybe I take too much time. Okay, so I have another question.
Sure.
I read one of your papers, the weekly balance one, the constant weight code, that yes. You're using modifications of the Knuth method. You have too many papers. I'm not sure you remember, but so in that paper you are solving a problems when the weight is not balanced, but there's an unbalance between 0 and 1. Sorry.
Okay.
So I'm concerning whether how large your unbalance, how large for the unbalance that you consider, like is it for every as large as you want, or the unbalanced one must be small? Have you considered the constant weight for any constant weight, or the weight must be close to half? Did you?
Yes, I understand your, sure. I understand your point. I think that, sure, I just explained that if you use balanced code words or fixed weight codes, then if you apply Euclidean distance detection, then the detector will be independent of A and B. Sure, you can easily show that. And actually, you can also show that Pearson distance and Euclidean distance for balanced codes are the same. The outcome will be the same. There's no difference between, so they're equivalent. Sure. But if only a small percentage of your code book is balanced and the other are close to balance, then I think that also the dependency of the reception quality on A and B will also be diminished. So if it is 100%, then it's completely independent. But if you have a small percentage of the code where the balance is very close to balance, then I think it will also be very helpful if you use the Pearson distance detection instead of the Euclidean distance detection. Sure. I think that would be an interesting topic to further study. Yeah, sure. That's very interesting.
Okay.
Oh, okay. Yeah. Thanks for having me. Yeah.
Okay.
So, any more questions? I think it's about the time. If no more questions, let's thank Professor Immink again for his fantastic talk and all the discussions. And also, this will be the end of the ITIS seminar series for this year. And we will put up the 2021 schedule very soon. So as mentioned earlier, it will be started probably in the late January. And we welcome you to attend the next batch of seminar series in 2021. Thank you.